Hey class, we are going to take a look at increasing and decreasing functions and the first derivative test in this section 3.3. Alright, so it says definitions of increasing and decreasing. Now, you know, the definitions that are given here, and if you took college algebra 2, basically, you know, it's the mathematical equivalent of just saying that as we read the graph from left to right, if our y-coordinates are getting smaller, then we know we're decreasing. If we're not changing, it's constant, and if our y-coordinates are getting larger, then the function's increasing. I think we're all okay with knowing whether, looking at the graph, and whether the function's increasing, decreasing, or constant. But the way that this is going to relate to what we're doing with derivatives, we know that if we a derivative function is a slope finder, and if a slope is negative, a slope of a tangent line is negative, that means that we have a decreasing function at that point. So whenever a function is decreasing, its derivative at any of those points along the function is going to be negative or less than 0. Okay? And just like when we talked about like finding horizontal tangent lines, that would imply that the derivative is equal to 0. So that would be where we're constant. We'd have a horizontal piece of the function there. And then if the derivative is positive or greater than 0, that means we have positive slopes. The function is increasing. Okay. All right, so the test for increasing and decreasing functions, and this is going to be closely related to our first derivative test for finding extrema. Let f be a function that's continuous on this closed interval and differentiable on the open interval, which that was the beginning of both our Rolle's theorem and mean value theorem from the last section. So we have a continuous and differentiable function. If the first derivative is positive or greater than 0, then the function's increasing on that interval. So if it's, if the derivative is positive on the open interval, it's increasing on the closed interval. If the derivative is negative, then we know we're decreasing. If the derivative is 0, it's constant. So that's what the graphic that we were looking at up here basically showed. Okay, so for example 1, it's asking us, it says find the open intervals on which this cubic function is increasing and decreasing. All right, so we're going to go based on the the definition of this theorem that we had up above. We want to find that derivative first, so we're going to find f prime of x. Okay, and with this function, we'll get 3x squared minus 3x for the derivative. We're going to set that equal to 0, so change that derivative f prime into 0, and we're going to solve that equation, and we can factor out a 3x to solve, x minus 1. So the two x coordinates, which give us derivatives equal to 0, would be that would be 0 for this 3x, if we set that, and then also 1. Okay, now the reason we're setting that equal to 0 to determine this is because if you look back up here, in order to change from decreasing to increasing or vice versa, at some point, and maybe it doesn't go horizontal for long, but we are at our lowest or highest points, the slope of the tangent line has to be horizontal, at least instantaneously. Okay, so that's where we want to put these values. So after we set that derivative equal to 0, okay, and we find the values for which the derivative does equal 0, those are our changing points, and that's going to be where we change from increasing to decreasing or vice versa. So once we have those, then we want to test the intervals around or between those where we get 0, or the zeros of the derivative, and because that will tell us we're going to be either increasing or decreasing in these intervals, and then it's going to be equal to 0 at those x coordinates. So let's test then. Let's find something in this interval. Let's just go with -1. So if I go f prime of -1, so I want to see if I get a positive or negative derivative for that. I would see if I plug that in, -1 into here, I am going to get 3 minus a -3, which turns out to be a +6. So this is positive here, and I usually just kind of draw something, so it looks like it's increasing, and it's not exactly the shape of the function, but I draw an increasing little ray there just to tell me, okay, that section's increasing. Now I need to test something between 0 and 1, probably 1/2, I guess. So let's do f prime of 1/2. If you do plug that in, you're going to get negative 0.75 or negative 3/4. So that is negative right there. We know that we're going to be decreasing if we get negative. So plugging 1/2 into our first derivative, we should see that we do get a negative value for that, negative 3/4. And now if we do something bigger than 1, let's just maybe go with 2. And I plug that into my first derivative, I'm going to end up getting also a positive 6 for that. So it changes back to positive. So for stating the intervals of increasing and decreasing, we would be increasing on the interval from, or intervals, negative infinity to 0. And then also, I'm going to do a union from 1 to infinity. So our two increasing intervals. Decreasing, our decreasing interval, the one we have is just between 0 and 1. Okay, so that's how we can do it. So we want to set our derivative equal to 0 and then solve that equation for the zeros. Now also, if there was a situation where the derivative was undefined, it is possible then for the function to change from increasing to decreasing there. So we want to solve for zeros of the derivative and where it's undefined, and I think we'll outline that here later. And then once you have those, then you want to test the intervals around those zeros to determine where we're increasing or decreasing. Positive test points are going to mean the function's increasing in that interval. Negative points that come out of your first derivative are going to tell you that the function is decreasing. Okay, so some guidelines for finding intervals on which a function is increasing or decreasing. And I just kind of went through the process before we talked about these, but what we want to is first know that it's a continuous function and it's differentiable, and that was a polynomial, so we knew that was true. Locate the critical numbers. Okay, so critical numbers, those are, we've talked about that before. Critical numbers are numbers that where the derivative is equal to 0, where it's undefined. And then we want to use those numbers to determine your test intervals. Determine the sign of f prime by picking a test value in those intervals, which we did. And then use the theorem for increasing and decreasing functions to determine whether the function increases or decreases. In other words, if the derivative is positive, it's increasing, and if it's negative, it's decreasing. Okay? All right, so it says these guidelines will also work if the interval AB is replaced with, all real numbers, I guess, if it's not just between necessarily two numbers, if it's the whole number line, or maybe it's from negative infinity up to a certain point. Sometimes maybe you're just working with the positive numbers or something like that. Okay, so terminology, it says a function is strictly monotonic on an interval if it is either increasing on the entire interval or decreasing on the entire interval. So I think we've maybe seen that before. Okay, so now the first derivative test. Now the steps for using this are similar to what we just did, but then we look a little more specifically at if we change from positive to negative or from negative to positive with our derivative, that will tell us whether or not we have a relative min or a relative max. So here in these pictures do a pretty good job outlining this. So right here we can see our derivative was negative, so we changed from a negative derivative to a positive. That means that we have a relative min at that point C. Okay, or at that x-coordinate C. Now in this drawing, if we change from a positive derivative to a negative derivative, again always reading from left to right, then that would mean at that point where it changed that we have a relative max. Okay, and then finally for like number 3, if it doesn't change, it's possible that we do, when we set the derivative equal to 0, we do get a horizontal tangent line here, but then it just continues to increase. Okay, so we may instantaneously just hit a horizontal tangent line, but then continues to increase. And so if there's no change, it stays positive on either side of C, then there's no relative min or max. And similarly, if it stays negative, there's no relative min or max. Example 2, I did leave the work on this one, or I worked it out ahead of time just to kind of save us a little bit of time, but we'll talk about the steps here. So this was a trig equation. So it says find the relative extrema. And when they do say find the actual extrema, that means the y coordinates as well. We'll have to figure out at which x coordinates those mins and maxes are, but then plug those in back to the original equation to get the y's. And our interval that we're working with, and because we know that trig equations are cyclical and they keep going on forever and ever, so there would be a number of relative mins and maxes. So here we're limiting it between 0 and 2 pi, which is convenient for trig equations. But to start off, same thing, we just want to find the derivative f prime of x, And so when we do that, f prime of x is just going to be 1/2 and then minus cosine of x for that one. And we're going to set it equal to 0, and we're going to solve for x, okay? So we're going to find the solutions for x in that interval 0 to 2 pi. So I'm going to move that cosine over to the left side of the equation, so cosine of x equals 1/2. And if you recall, with our when we solve these trig equations, I want an adjacent to hypotenuse ratio to equal 1/2. And so if I were to draw that triangle out, it would be a 60-degree angle, which in radians, that's going to be pi over 3. Okay, so pi over 3 is our one, and there's pretty much always two answers to these. Since cosine is positive in both quadrants 1 and quadrant 4, wherever the x's are positive, then we have to use that 60-degree angle as a reference angle in quadrant 4, which would be at 300 degrees. In radians, that's 5 pi over 3. So these are our two solutions that make the derivative equal to 0. Okay, so that's what we're going to test, and I'm putting 0 and 2 pi as my ends on there because we're just looking in that interval. So we want to test an angle that's between 0 and pi over 3, between pi over 3 and 5 pi over 3, and then between 5 pi over 3 and 2 pi. Okay, so I have 3 intervals to test. So in the first interval, I picked pi over 4. It's another common angle, a 45-degree angle. Now if I were to plug that in, so if I'm doing f prime of pi over 4, plug that in here, I end up with 1/2 minus the cosine of pi over 4, which is root 2 over 2. And 1/2 minus, now root 2 over 2 is about 0.7, and so that's going to turn out to be a negative value. 1/2 minus 0.5 minus 0.7 is going to be a negative, approximately 0.2, something like that. Okay, in this interval between pi over 3 and 5 pi over 3, I'm testing pi over 2, which would be 90 degrees. And so if I put that in there, well, the cosine of 90 degrees is 0, so I just get 1/2 minus 0. That's positive then. So I get positive here. So I've got negative, which is decreasing, positive, which is increasing. And then finally, I'm going to test 11 pi over 6, which is another common, that's 330 degrees. So you have like a 30-degree reference angle, but it's in quadrant 4. So if I put 11 pi over 6 and I take the cosine of 11 pi over 6, that is also a positive, let's see here. Oh, that's actually, it's root 3 over 2. Okay, so we're taking 1/2 minus the cosine of 330, which is the equivalent of a 30-degree reference angle. So that ends up being root 3 over 2. And so root 3 over 2 is like 0.86, 866, something like that. And so this ends up being negative again. 1/2 minus 0.866 is negative. So we get negative there. So looking at this, if you visualize this, we go from decreasing to increasing, there's going to be a relative min at pi over 3. We go from increasing to decreasing, at 5 pi over 3, there's going to be a relative max there. Okay? So relative min at pi over 3, relative max at 5 pi over 3. Now, to get the actual values, we need to take and plug these angles into the original, right? We're talking about the actual point on the original function. The first derivative was used to tell us whether or not we have positive or negatives, telling me whether it's increasing or decreasing. But to actually get the point, we need to plug into the original, okay? So when I plug pi over 3 into this original function, I end up getting pi over 6 minus root 3 over 2. And when I plug in for the relative max, 5 pi over 3, when I plug that in there, I get 5 pi over 6 plus root 3 over 2, okay? And so that's how we can do applying that first derivative test to figure out some relative extrema, all right? Here's another example for determining some relative extrema. So this one, it's like kind of like a radical expression because it does have the fraction exponent, which is like a cube root and then something squared. But for doing the derivative, it's probably good to leave it in this form to start. So f prime is going to be equal to 2/3 and then x squared minus 4. We take one away from the exponent, so that gives us negative 1/3. Now in this case, we do need to apply a chain rule because we did that exponent rule, but what was inside of here, we have to take it times that derivative as well. So the derivative of x squared minus 4 is times 2x. So we have to do that as well. Now if I simplify this, it's going to look a little more like, the 2x here in this 2 numerator of the 2/3, we'd multiply those together, put those in the numerator, and the other pieces are in the denominator. The 3's down there, and then this negative exponent's going to drop that expression down into the denominator. And you know, the 1/3 power is kind of like a cube root. That'll probably be easier for calculating if I think cube root. Then I've got x squared minus 4. So that is my derivative, and I am going to set that equal to 0, right? So I've got 4x over the cube root of x squared minus 4. I want to set that equal to 0. Now, remember that we're looking for anything that makes the derivative equal to 0 or undefined. Our critical numbers are going to be, you know, so when you have a fraction like this, you want to set both the numerator equal to 0 and the denominator equal to 0. Those are all your critical numbers. So zeros of the numerator are zeros of the function, zeros of the denominator are where you get undefined in your, and you know, those are also critical numbers because undefined derivatives can mean, it could mean that there's a vertical asymptote, but it could also mean like there's a sharp corner or a cusp there, okay? All right, so if I set 4x equal to 0, obviously that's just going to be 0 for one of my critical numbers. And if I set the denominator, this, oh, sorry about that. I should have had a 3 down here as well, because of the 2/3, that would still have a 3. I actually omitted that. Okay, so it's 3 times the cube root of x squared minus 4. I want to set that equal to 0. It doesn't necessarily matter all that much because we're just going to divide that off, and it's going to end up disappearing anyway. So if I would divide by 3, that's just going to be gone, but I should have it there. And then x squared minus 4, the cube root of that equal to 0. And here I would like cube both sides to get rid of the cube root. Now I've just got x squared minus 4 equals 0. So I'm going to get x equals plus or minus 2, 2 and negative 2 there. Okay, so those are all my critical numbers, 0 and then 2 and negative 2. So let's put those on number line. So I've got negative 2, I've got 0, and I've got 2 on there. And I'm going to test each of these intervals, something in this interval between negative 2 and 0, between 0 and 2, and then greater than 2. So let's just do f prime of negative 3. And if I plug that into my first derivative over here, I'm going to get a negative on top. I'm going to get a positive on the bottom. Negative over a positive is going to be a negative. Okay, so that'll be negative right here, negative, decreasing. Okay, if I test f prime of negative 1, I'm putting this into my derivative right here. I'm going to have a negative on top. I'm also going to have a negative on the bottom because negative 1 minus, so negative 1 squared is positive 1. 1 minus 4 is a negative 3. So I've got a cube root of a negative, which is still a negative. You can take cube roots of negatives. And so you end up with a negative over a negative. That's going to be a positive for that one. Let's pick f prime of 1 now. So if I put a positive 1 in there, that means I'll have a positive on top, and I'm just going to have a negative on the bottom, right? Because it'll work out the same way that the bottom did here. We square that positive 1, we have negative 3, cube root of that. So positive over negative is a negative there. And then finally, f prime of, let's use 3 in that last interval. And with that, we're going to get positive over positive. That's positive. Okay, so we had positive here, increasing. We had negative when we tested a 1, so that's decreasing. And we had a positive here, which is increasing. Okay, so to sum this up, we can see we've got right here at negative 2, that's going to be a relative min. At 0, a relative max. And at 2, we've got a relative min, it appears. Okay. And we are supposed to find the extrema, so let's see. So relative min, or mins I'm going to say, is going to be at x equals negative 2. If I plug a negative 2 into my original, I end up getting 0, and so that is 0. I'm going to, that's my y-coordinate. The relative min at x equals negative 2 is 0. Another relative min, x equals x equals sorry, our other one was at x equals 2. At x equals 2 is, we plug that 2 in there, we're also going to get 0 again. So we get 2 of the same relative mins. And then relative max relative max. There's only one of those we can see is right here at x equals 0. If I plug 0 in there, I'm going to end up getting, it's like the cube root of 16 if I plug 0 in here. So it's 0 minus 4 is negative 4. If we square that, we get 16, and we end up taking the cube root of 16. So is the cube root of 16, that's not a rational number, but approximately 2.520. Okay, so those are our relative extrema for this problem, and hopefully you're following how we're locating those. Okay, and the last one, we can get through this last one I think in this video. Okay, so with this one, I would, before we do the the derivative, it might be easier to rewrite this so we don't have to use a quotient rule. If we divide each term by x squared, that would leave us x to the fourth over x squared is x squared. 1 over x squared would be x to the negative 2, and then f prime is going to be 2x minus 2x to the negative 3, like that. Okay, so I'm going to set this equal to 0. So 0 equals 2x minus 2x to the negative 3. And, well, for solving, maybe I'll call that 2 over x to the third, like that. It'd be easier for solving. To solve this, I think it's going to be easier just to get a common denominator for this and just have one fraction, and then we can find the zeros of the numerator and the denominator like before to find all of our critical points. Okay, so zeros of the derivative and where the derivative is undefined. Okay, so if I rewrite this, I could call this, this could be 2x to the fourth over x cubed would be the same as this. So 2x to the fourth minus 2 all over x cubed would be equivalent to what I have up here. And so if I set the numerator equal to 0, if I were to set the 2x to the fourth minus 2 equal to 0, and then also the x cubed equal to 0 for the denominator, and I'm going to x to the fourth equals 1, and so that means I'm going to get plus and minus 1, so x equals plus or minus 1 for that part, and for the bottom part, x equals 0. Okay, so if we test there, I'll put those numbers on here. Now, something else to look at when when I'm finding, especially what makes the derivative undefined 0, you want to look at the original function and see, okay, well, when x is 0, is there actually even a point there? No, it's a vertical asymptote, because you can see in the original function as well, when x is 0, it's undefined. So you are going to have a vertical asymptote at 0, and so I would recommend kind of drawing that in like that. And then we have -1 and +1 as our other critical points. Now, just to kind of go back to this one, we did have, what did we have for zeros of the denominator? We had -2 and +2, and those actually, they didn't give us any vertical asymptotes or anything like that. So it's not always the case that whatever makes the derivative undefined is also makes the original function undefined. In this case, it did, though. So I put a vertical asymptote there, because what we're doing is just doing like a rough sketch of what's happening with the actual original function. Okay, so now let's do some testing. Let's test f of, let's go probably -2, or f prime of -2. Let's do f prime of probably -1/2. We're going to do f prime of +1/2, and f prime of, let's just do 2. Okay, so in the original, if I do -2, so that's going to give me, what am I going to get if I put -2 in there? We're testing it in here, okay. So what's going to be the easiest one to test in? Probably this one is easier to test, just because it's all one fraction, I think. Then you can just think sine of the numerator divided by sine of the denominator. So if I put a -2 in here, it's going to be like a positive, definitely a positive numerator, because you've got x to the fourth here, and then a negative denominator. So that's going to be negative. Now for f prime of -1/2, Well, okay, if I do negative half, that's going to be like 1/8 when I take it to the fourth. No, that's going to, sorry, it's going to be 1/16. So it's going to be like 2/16 minus 2. That's negative on top. And the bottom's going to be also negative. Negative over negative is going to be positive there. If I do a positive 1/2, we're going to have, if I do a positive half, I'm going to have a negative on top, but a positive on the bottom. So that's going to be negative. And if I do a positive 2, well, that's just going to be positive over positive. So I'll have alternating signs again. So we're going to go from decreasing in this interval to increasing. This will be decreasing, and this will be increasing. Okay, so it looks like we're going to have relative max at -1. Oh, sorry, that's where my relative min is. Relative min at x equals -1, and if I plug -1 into the original function, I'm going to get a positive 2. That is 2. And relative, another relative min, we don't have any relative maxes, right? It goes from decreasing to increasing, and then increasing and decreasing here, but it's undefined, so we don't have a relative max because the function is actually undefined right there. There's no point, it's a vertical asymptote. But then here again, we change from decreasing to increasing at +1. So there's another relative min, I should say mins, at x equals -1 is 2, and at x equals +1 is also going to be 2. We're going to get this in. So we have 2 relative mins, both equaling 2, one of them at -1, one at +1. Okay, so that's basically it. That's what we're going to be using this first derivative test for. So you're setting your first derivative equal to 0, you're finding the critical points, you're testing in the intervals around those critical points to determine if you have positive or negative first derivative, increasing, decreasing, and we're looking for if it changes from decreasing to increasing or vice versa, whether or not we have relative mins or maxes. Now, down here we have the actual graphs of these curves that we just looked at, which is kind of nice to look at this again. If we looked at the graph of this first one, we would have had we've seen that we had a relative min, at a certain point here. This was our pi/3, I think, and then our relative max here at 5 pi/3, and that was, if we did graph these out, we'd see that, and we determined that through our first derivative test here. Came up with the specific y coordinates. The second one, this one is kind of interesting because it was, we did have some critical points where the derivative was undefined, and the reason for that, it's good to point out why that was. At the 2 and the -2, those were zeros of the denominator of the derivative, which meant the derivative was undefined. And what's happening with the graph there? The reason the derivative was undefined is because we have what's called a cusp here. This graph is kind of funky looking, but so we get like it's almost a sharp corner. They call it a cusp when it goes from a straight line to like a curve. But yeah, so it can change from decreasing to increasing or vice versa at a cusp as well. And as that turned out, these both were relative mins there, and our relative max turned out to be at 0. And then the last one we just looked at, we had 2 relative mins, and then the x equals 0, this was a vertical asymptote right there. Okay, so that's it. That's our notes for section 3.3, first derivative test, increasing and decreasing.